Welcome to the lecture for Pre-Calculus Section 4.3 on solving rational equations. The first thing we're going to talk about is your classic inverse variation problem, because this is a problem that gives you variables in the denominator, which after all is what a rational equation has. So this problem says, suppose y varies inversely with x. We'll start with that part of it. So the way that we write that, we say y varies inversely with x. Okay, that means if x goes up, y goes down. If x goes down, y goes up. That's what we mean by an inverse variation. Conversely, if you were talking about a direct variation, x and y would both vary in the same direction. If x goes up, y goes up. If x goes down, y goes down. But it doesn't happen that way with an inverse variation. It's in the opposite direction. So we have what's called a constant of variation here, and that gives you your relationship between x and y. Basically tells you what that up and down, how much up and down we have with this x and y in this problem. Okay, so the first thing that we're given is that y is equal to 80 when x is equal to 4. So this right here fully defines your problem. I like to call this a full set of values. Okay, we use our full set to find out what k is for our given problem. So if I plug 80 in for y, not knowing k yet, and I plug 4 in for x, I'm able to calculate what my constant of variation is. Ties these two numbers together. So if I do cross multiplication, I'm going to get k times 1, which is k, is equal to 4 times 80. So k is equal to 320. Okay, so now I know what the relationship is between x and y in my problem. So let's put your k in here. 320 would replace k. So now, if you're given an x, you can find the y. If you're given a y, you can find the x, because this is your relationship for this problem. All right, so we have another part of this problem that says, what is the value of y when x is 12? So we're given the x value. We want to calculate the y value. So y is equal to 320 divided by 12. All right, let's reduce that. 4 goes into 12 3 times. 4 goes into 32 8 times, so 80. So y is equal to 80 thirds. So when x is 12, y is equal to 80 thirds. So these kind of problems are two-step problems. First, you use your full set to find your constant of variation. Then you write your equation with the k substituted into the equation. And then you answer the question, what is the value of y when x is given? Or it might say, what is the value of x when y is given? This next problem is an example of an inverse square relationship. So this says the force of gravity on a rocket varies inversely with the square of its distance d from Earth. So we have two variables again, f and d, and this is key square, and this is key inversely. So we say f varies inversely with the square of its distance d from Earth. Square of d. Inversely means I put it in the denominator. Okay, you always have that constant of variation. So since it says it varies inversely, you put your d squared in the denominator. Since it says it varies with the square of d, you put d squared in the denominator. Next, we look and see if we have a full set so that we can evaluate k. So a full set would mean I'd need f defined and d defined. So here it says if f is 10,000 pounds, when d is 1.3 miles. All right, the other part is the question part. What is f when d is given? So first, these are two-step problems. We need to find the k using the full set. So make sure you're taking good notes on this. So let's substitute 10,000 for f. We don't know k yet. This is step 1. But d is 1.3. And we square that. So we're going to say k times 1 is k, is equal to 10,000 times 1.3 squared. So we get k is equal to 16,900. All right, so now we can write our equation as f is equal to 16,900 over d squared. So this is our equation. Now we can answer the last part of the question that says, what is f when d is 1.75 miles? So what is f? We don't know f. K, 16,900. D is 1.75. Then square it. So this is 5518.4. The units of force that we're working in are pounds. So F is 5,518.4 pounds. Once again, to summarize, the first step of this problem is to use your full set to find your K, your constant of variation. Your second step is to answer the question being asked, what is F when D is given? Or it could have said, what is D when F is given? Either case. Before I get into example 3, I just want to remind you how adding and subtracting fractions works. So if I was going to do this simple problem here, 2/3 plus 5/8, I can't do that unless I have a common denominator. So if I look at the 3 and the 8, I want to come up with a common denominator. So I'm going to say 24 would work. And that's because I can multiply this fraction by 8 over 8, which is a form of 1, which won't change the magnitude of my fraction 2/3. And I could multiply 5/8 by 3 over 3, which is also a form of 1, which won't change the magnitude of 5/8. But what it will do was allow me to have a common denominator. So I've got 2 times 8 over 3 times 8 plus 3 times 5 over 3 times 8. And now I have a common denominator. 24 and 24, they're the same. So I can go ahead and add those up. So I'll get 31 over 24. Now let me just point something out here. And this is critical to the technique we use once we set up the common denominators in rational equations. We can look at only the numerators here, and we can say that that is a true equation. 16 plus 15 is indeed 31. So 16 24ths plus 15 24ths equals 31 24ths is true, but also just the numerators themselves is a true equation. So if we can get the denominators the same, we can use the numerators to solve for the missing variable. And I'll show you how that works. So let's solve this problem by getting a common denominator and then using the numerators to solve for the missing variable. So first I'm going to turn 1 into a fraction by putting a 1 on the bottom. And I'm going to rewrite the rest of it. Oops. And I'm going to choose a common denominator. So I've got n plus 4 here and here, so it makes sense to get n plus 4 here as well. So the way that we introduce that n plus 4 is to multiply this fraction by n plus 4 over n plus 4, which is 1. So that won't change my original fraction, 1 over 1. So now let's go ahead and take off the numerators and make an equation using only the numerators, and I can do that now because I have a common denominator in all three fractions. So on the left I have n plus 4 times 1, that's n plus 4. Then I have 1. Then I have minus n plus 6. Be very careful that you remember that this minus here must be distributed to both of these. All right? That's a common mess-up place. Be careful there. Make sure you're taking notes on these problems. So I have n plus 4 is equal to 1 minus n minus 6. All right, so this is n plus 4 is equal to 1 minus 6. That's negative 5 minus n. So let's bring all the n's over to one side. So I've got 2n plus 4 is equal to negative 5. And I will bring the 4 over to this side. I've got 2n is equal to negative 9, and then divide by 2. So n is equal to negative 9 over 2. Okay, so we found out what n is. Now we want to verify that that is indeed a solution to this problem. And the way I'm going to do that is by substituting negative 4.5 into my original equation. You have to be careful. You check for extraneous solutions when you're solving rational equations. Usually what will happen if it's going to be a problem is you'll get a 0 in the denominator or something like that. But I'm going to go ahead and substitute it in here. So I need to have a 1. So 1 over negative 4.5 plus 4. And then n plus, oops. So I went ahead and wrote all that out just to save some time. But what you do is you just substitute it in there, and you could use a calculator if you needed to. I didn't, but I found that negative 0.5 is equal to negative 0.5 by plugging in my answer here. So I would say yes, good. This is my solution. N is equal to negative 9 over 2. Okay, so this problem here is a little bit more complicated. The first thing you want to do is factor the denominators to help you determine what your common denominator should be. So I'm going to say, let's space it out a little. So I've got 3x minus 3. All right, now let's figure out the factors here. So I have 10, 1 times 10, 2 times 5. And I need to get a positive 7 in the middle. So it must be 2 and 5, leading coefficient of 1. So I don't have to factor by parts. So that would be x plus 2, x plus 5. All right, and then I've got equals 1 over x plus 5. I space it out a little. And then I've got that same quadratic in the bottom, x plus 2, x plus 5. All right, so what I can see here is that I need to have x plus 2 and x plus 5 in the denominator, and I have them here, and I have them here. I have one of them here. If I can get an x plus 2 here, then these will match. Same. So we do it the same way. We multiply by 1. In this case, my 1 is going to be x plus 2 over x plus 2. And then I'll have matching denominators. All right, so my next step is now to write my equation in terms of the numerators only, now that I've got the common denominator. So on the left, I've got 3x minus 3 is equal to 1 times x plus 2, that's just x plus 2, plus 1. So that's 3x minus 3 is equal to x plus 3. So I'm going to subtract this x over to here, and I'll get 2x minus 3 is equal to 3. So add 3, I'll get 2x is equal to 6, or x is equal to 3. Okay, so now I want to go ahead and I want to substitute it back into my original equation and see if I have a true statement. If not, I'll have no solution. All right, I sped this up a little. I substituted 3 into my original equation. You have to go all the way back to the original equation to check it. I substituted in on the left and the right side. I got these numbers here so far. Now I can get, let's multiply this by 5 over 5. So I've got 6 over 40 is equal to 5 over 40 plus 1 over 40, which is equal to 6 over 40. Okay, so that checks. So your answer is x is equal to 3. And you always want to plug back in your answer that you think it is to verify that you don't get an extraneous solution. Remember, an extraneous solution is one that appears to be a solution, but when you plug it back into your original equation, there's a false statement that you arrive at. Okay, in that case, it's not a solution, no solution. Okay, here's another problem. So this one doesn't need to be factored. So let's just spread this out a little bit here so we have some room. All right, so what I've got in the denominator here, 2, 2n, and 2n squared. Okay, so you can't decrease the number of things in the denominator, but you can increase the number of things in the denominator. So I'm going to have to take this one and go up to n squared because my tool is multiplication. So with multiplication, you can only increase the stuff that you've got. All right, so I need to go to 2n squared. All right, I got the 2, 2, 2. It's just the n's that I need to get in there. So I need another n here. So this is 1. And I need 2 n's here. So this is 1. So I'm always multiplying by 1. All right, so now that I've got 2n squared here, 2nn is 2n squared, and here, I can go ahead and make my equation using the numerators. So on the left, 1n squared. So we got to distribute this n, 2n plus 6. This one is just 1. So this is n squared is equal to n squared plus 6n plus 1. So minus n squared. So it's not going to be a quadratic, which sometimes they can be. So I have 6n is equal to negative 1. So I have n we think is negative 1/6. Right, so let's check it. So I went ahead and substituted negative 1/6 into the original equation and found out that I did get a true statement. So n is equal to negative 1/6. Okay, so you want to go ahead and check your results on these and make sure that you get a true solution. Otherwise, you're going to say no solution. All right, so here's another example. So I want to make sure I'm writing a 1 underneath my 1 to make it a fraction. I'm just going to spread this out a little bit. And I need to factor where I can on the denominators. So I got a GCF of k. So this would be k plus 3. So you want to factor the denominator to help you find your common denominator. All right, so now I'm going to look and see what I've got. I've got a 1, I have a k plus 3, a k times k plus 3. So remember, I can only increase the things that I have in my denominator. Okay, I can't take them away. So it looks like I've got two things, a k and a k plus 3. So here I've got a k plus 3, so I need to get a k in there. So multiply it by 1. Now I have k and k plus 3. But over here, I need them both. I'm missing all of those, both of those, k and k plus 3, k and k plus 3. So this is 1. So I'm multiplying by 1. Now if I look and see, I've got k times k plus 3, k times k plus 3, k times k plus 3. So I'm ready to take off my numerators and make an equation. So here I've got k times k plus 3 minus k times k, that's k squared, is equal to, on the right, 6k plus 36. So that's k squared plus 3k minus k squared is 6k plus 36. These will cancel. So 3k is equal to 6k plus 36. 6k. So minus 6k. I've got negative 3k is equal to 36. Divide by negative 3. I have k is equal to negative 12. All right, so let's check it. So I want to substitute negative 12 back into my equation and see whether I get a true statement. All right, so I paused it while I did those calculations. So I substituted in negative 12 into my original rational equation. I got a true statement. It checks. So my answer is k is equal to negative 12. So I have one solution. All right, this is the last example I have for you. And in this example here, we're dealing with quadratics. So the problems I've given you, you're going to either have an x to the first power equation or an x to the second power equation to solve. So first thing we're going to do here is we're going to find the factors of x squared plus 2x minus 3. So 1 and 3, I need a positive 2 in the middle, and they need to multiply to give me negative 3. So x minus 1, x plus 3. All right, so those are my factors I need. Now, if I look over here, I've got an x minus 1, and here I have an x plus 3. So each of these is missing one of the factors. Remember, I can only add factors, so I need to multiply this one here by x plus 3, x plus 3, and I need to multiply this one here by x minus 1, x minus 1. So this is 1, this is 1. So I'm going to, on the top, I'll have x plus 3, x plus 1. All right, I'm only using my numerators now that I have a common denominator. All right, and then I have only an 8 here because I didn't have to multiply over here by anything. All right, so let's simplify that. So I'm going to double distribute. I'm going to combine like terms. So we're going to bring the x's over to this one side over here. So I'll have x squared plus 9x plus 3 is equal to 13. Okay, I'm going to have to solve a quadratic here because I am retaining my x squared. So bring the 13 over so all of our terms are on the left, and we'll have a 0. X squared plus 9x minus 10 is equal to 0. Okay, so we're going to have to solve this quadratic. Let's see if it's factorable. So I've got 1 times negative 10, 1, 10, 2, 5. I need to add to get 9. So leading coefficient of 1. So I can write my factors in, x minus 1, x plus 10. So this factor will give you a solution, x is equal to 1. This factor will give you a solution, x is equal to minus 10. Okay, so let's be very careful that we check our solutions here to make sure we don't have an extraneous solution. So going back up to the top here. Okay, so I erased to make some room. I'm going to check my two solutions, 1 and negative 10. So if I look at my original equation, all right, so I cleaned it up a little. So if I check 1, what's going to be clear immediately is if I put 1 in here, 1 minus 1 is 0. I'm going to get a 0 in the denominator of this fraction here. So I can't say that 1 is a solution here because it's not in the domain. Okay, so 1 is a domain restriction. X cannot be 1. All right, so now let's check this solution here. X is equal to negative 10 to see if it checks. All right, to speed things up, I plugged it in. So I plugged negative 10 into our original equation. I carried out the simplification. So 63 over 77 equals 55 over 77 plus 8 over 77, and that is equal to 63 over 77. So we have one solution, and this was an example of how you can be required to solve a quadratic equation in the end. And another thing that happened on this one is that one of the solutions was an extraneous solution. This x is equal to 1 ended up being an extraneous solution. So we have one solution, x is equal to negative 10. Okay, so I hope you took good notes. These problems are representative of what you'll see in the homework set. Let me know if you have any questions as you work your homework set.